Good morning. So, today we are ready to begin our class. As you all can see, we are again having a new setup, and I hope this particular setup works well for us. Is my sound audible? Please let me know if the sound is audible. So, hopefully, everybody can hear me, and let us start our class. So, as we have been discussing, we have already completed the first three Maxwell's equations. We have seen that they can be changed from the differential form to integral forms and vice versa. We have also discussed about their physical significances. And today we are ready to talk about the fourth Maxwell's equation. So as you can see that the points which I would be discussing today will be the fourth Maxwell's equation. And this particular equation is also known as the Modified Amperes Law. So while we are discussing this, first we will discuss what is the so-called Amperes Law. Then we will see why there was a requirement of a modification at all. And then from there, finally, we are going to learn about a very new concept called displacement current. So these are the topics which are the intended outcomes of this class. Fine. So now, if you are all set, let us begin the discussion. So what we are going to start with is, let us recall that what did Ampere basically tell us in the beginning? What is the so-called Ampere's law, or we also call it as the Ampere's circuital law. And once we have discussed about this Ampere's circuital law, then we will move forward to its modification. Okay. So now let us jump into our topic. So what did Ampere say? Now all of you know that electric current has a lot of effects. One among such effects is creation of magnetic field, right? So when there is a conductor carrying current, there will be a magnetic field produced close in the vicinity of it. So as per the Ampere's law, suppose I have a wire which is wire made up of a conductor obviously. So if there is a current carrying conductor and there is a current I flowing in that circuit, as per Ampere's law, this current will produce a magnetic field around it. And how much will be the magnetic field? If I want to know what is the magnetic field at say this point, then what I can do is I can construct a loop, a closed loop across this point. So suppose this is my wire, the loop will be like this. So right, the loop can be constructed like this, and at any point on this loop, we will be able to calculate the magnetic field with the help of the formula or the law which Ampere told us, that the line integral of this magnetic field which we want to find out in this closed contour is just the current multiplied by the permittivity of free space mu 0. So B dot dl calculated over the closed contour is nothing but mu 0 I. So as per this law, what we are able to see, that if there is current, that is if this I value is non-zero, there will be a magnetic field created. Also from here, we people used to think at that time that if this current goes to the value 0, in that case the magnetic field value also will go to 0. So this was the so-called Ampere's circuital law, and the law was working fine until a point when the alternating current was discovered. And how did it pose a problem? Now let us try to understand this fact first. I will be telling you about an experiment which was done, and from where the problem or the lacuna of this Ampere circuital law was found. So let us try to see what that experiment was about. So that was say a very simple circuit can work in this case. Say I have a circuit with a parallel plate capacitor connected to it. But remember, the voltage source that we are now going to use is an AC source. Alright. So in this scenario, what will we see? Now remember, this this parallel plate capacitor that we have used here is not having any medium inserted inside it. It is just having air. Alright. So the experiment which was done at that time, was designed in that manner that the parallel plate capacitor was only having air inside. There was no so-called dielectric medium inside it. Now what happened? Now the moment this AC source is switched on, what do we expect? That current will start to flow in the circuit. And this current is the so-called conventional current I. Now, as per Ampere's law, anywhere around this wire, when the current is flowing, there will be a magnetic field. And in order to test this, what was done? Suppose there was a magnetic needle placed over here. A magnetic needle, as you all know, is a very small device which can sense current. It shows deflection when there is a presence of magnetic field. Now, suppose somewhere near the wire, when the magnetic needle was placed, the needle showed some deflection, indicating the presence of magnetic field. And this was expected as well. But the unexpected result was actually found when a magnetic needle was kept in the void space where there was no conductor. And very surprisingly, it was observed that even when here in between these two plates, even when there is no presence of a conductor, the magnetic needle showed deflection as well. So just try to imagine. If I write the Ampere's circuital law, we have already discussed that if current is present, magnetic field B will also be present. But there was this surprising observation that in the space where there was so-called no current, because there was no conductor, the presence of magnetic field was detected. So this was very surprising, and the scientists had to think or had to draw the inference that there must be something wrong or rather incomplete in this Ampere's circuital law. And this is where Maxwell stepped in. Maxwell actually introduced a new term or a modification in this law and finally completed it. Now see, let me just add a point over here that Ampere's circuital law holds good for steady state current. What do I mean by steady state current? Steady state current means the current that doesn't change with time, or the source doesn't change with time, which means DC. Fine, it was nice. But the problem arose because of a time-dependent current, where the current was varying with time, was changing with time. And that was because it was an AC source. Remember, the AC, it flips, polarity flips, right? So that was the cause. So when we are finding out or when we are talking about the modification in Ampere's law, remember we are talking about a non-steady state source. All right, it is actually applicable for that. Now, in this scenario, what did Maxwell tell us? Now, let us try to understand that fact first. As per Maxwell, he said that the moment I am turning on this source, what is happening at the plates of the capacitor? We will expect that, say, at one instant of time, this plate will be a positive plate and the other plate would be a negative plate. So in this scenario, I hope all of you will agree with me if I start to tell you that an electric field has been set up between the two plates, isn't it? And the direction obviously will be drawn from positive to negative. So what is happening? This voltage source is creating an electric field. However, what is the nature of this electric field? Say we are using an AC source of 50 Hertz. Then what does this mean? That in 1 second, this polarity is going to flip 50 times. Which means this electric field that has been created by this source is not a steady state source. It is going on changing with respect to time. Say in case of 50 Hertz, 50 times a second. Which means there is, say, like a time dependence of the electric field. Remember, who has caused this electric field? The AC source has created the electric field. And this field is not a constant in time. This is having a change. It is changing with time. Fine. Now, as per Maxwell, this changing electric field causes a new type of current. He argued that current produces magnetic field very good, but the belief that this current is only produced by moving charges may not be completely true. He said that if moving charges can create current, there is another possibility as well. And what is that possibility? That possibility is something like this, that whenever there is a time rate of change of the electric field across the plates of the capacitor, then there is production of a different type of current within this space. And this current has caused the magnetic needle to deflect. And he called this particular current as the displacement current. He used the term displacement current, ID. All right. So as per this modification given into the Ampere's law, Maxwell wrote the new modified Maxwell's law as modified Ampere's law as B dot dl is equal to mu 0 IC plus ID. Please note the value that this ID over here is this displacement current, which was newly introduced by or newly told to us by Maxwell, whereas this IC is the so-called conventional current, the conduction current, the current which is occurring because of the conduction of moving charges. So this is our known current, and this is the new factor or the displacement current. And as per Maxwell, the movement of the magnetic needle within the parallel plate capacitor has been caused because of this current, this displacement current. Okay, so this is how the modified Maxwell's law looks like. All right, I suppose there are no more questions, so we can just move forward. Now, in this scenario, now you might be wondering that what is this ID? What is the value of this ID, right? So now let us try to see that how Maxwell gave the magnitude or the value of this ID or the displacement current, right? So now let us begin that. So all of you must remember, if you go back to your electrostatics classes or the earlier knowledge of electrostatics that you all have, that if I have a parallel plate capacitor, the electric field produced by this parallel plate capacitor is given by E is equal to the charge Q epsilon 0 into area. Right? Do you all remember? See, I'm not going into the derivation of this particular thing. This is very easy. You just turn the pages or just see the earlier books. You will be getting it very easily. What I want you to just tell you now is that let us try to understand what are the facts over here. What are the terms over here? So this E is the electric field produced by a parallel plate capacitor when it has been provided with a voltage, right? Now Q is the charge that it has accumulated. Epsilon 0, we all know permittivity of the, of free space, and this A is the area of these plates, area of the parallel plate capacitor. So in this scenario, Maxwell began his calculation from this equation. He said that this electric field has been created, fine, but this electric field is not fixed. It is changing with time. And how is it changing with time? It is changing with time as del E del T. Now you might be wondering over here, students, that why am I writing del E del T? Why not del B d E dt? Instead of d E dt, why have I used the term of or the partial derivative del E del T? Now, it is actually the reason that electric field may vary because of two reasons. See, it is a function of position as well as time. In this case, since it is only varying with time and we do not know, we are not talking about the aspect of the position, we are only doing the variation as a partial derivative. So, the usage of del del T. Alright. So, if E is Q by epsilon 0 A, what will be del E del T? Obviously, since the area of the plates is not changing, epsilon 0 is a constant, we all will be able to write now that this will be nothing but this. So, del E del T is 1 by epsilon 0 A del Q del T, and this del Q del T over here, this del Q del T over here is the one which was identified by Maxwell as the so-called displacement current. This he replaced or told us that this value is our displacement current. So if I just write it over here in a little better manner, this time rate of this thing was identified by Maxwell as ID. So in this scenario, I hope all of you will agree with me and with Maxwell as well that ID can be written as epsilon 0 A del E del T. So now here see, we are having the mathematical value of the so-called displacement current. Now you might be thinking that why was the term displacement current used? Why did Maxwell call it as displacement current? Let me give you a clue. See over here, what are the terms? I have epsilon 0, area, E. Now this epsilon 0 is a constant. So by my choice, if I write it like this as well, I am right. I have not done any mistake. But then epsilon 0 E, what is epsilon 0 E? Epsilon 0 E, my dear students, if you remember, is nothing but the displacement vector D, right? So, because of the change of this displacement vector only, actually the current was originated and hence the name was termed as displacement current. Alright, so is this clear to all of us? The name behind this so-called displacement current, because it is actually arising because of the factor epsilon 0 E, nothing but the displacement vector. Right, so I'll again get back to the original notation of say epsilon 0 A del E del T. Or we may not also write the vector part. So this is where we are now standing. So as per Maxwell, the time varying this time varying source, this AC source is creating a time varying electric field, and this time varying electric field is giving rise to a new type of current called the displacement current. This is, remember, this is not the so-called current due to the movement of charges. It is a new type of current which has been arise, which has caused by the time changing electric field across the plates of the capacitor. All right. So this is where we are now standing. Now with this concept or the knowledge of the value of displacement current, let us get back to the Ampere's law. Let us get back to our Ampere's law. So what I can write over here? So as per Maxwell, B dot dl across the closed contour C is now mu 0 IC, the so-called conduction current, plus epsilon 0 A del E del T. This one we had earlier called as the ID. Right? So this is how the modification in the Ampere's law was done by Maxwell. Now, you all can say that this is the so-called integral form of Maxwell's law because we are directly seeing the integration over here. We can also write it in a little different manner. Let me show you that now. All right. So what is that? Now let us come to this particular term of IC or the conduction current. Now, suppose this is my conductor. This is my so-called conductor. This conductor is now letting the charges flow through it. So in this scenario, can I not consider that this current can be written as, say, first let me write it down and I hope you will agree with me that can I not write it as JC dot ds over a surface S, which means, say this is the cross section of my conductor, this is the cross section of my conductor, then across this surface, the current which is flowing through this surface can be written as a quantity called Jc into ds, and I hope all of you will agree with me if I call this J as the current density, surface current density. Isn't it? We all can write this. What we have done? We have taken the charge density, the surface charge density, we have multiplied it with the surface. So that will give me my total current, right? So if I use this particular format, so instead of just because I am trying to write down the integral form of Maxwell's fourth law, what I am trying to do is this IC I am writing it again in terms of an integral. Okay, so that a uniformity is maintained. So I hope all of you will agree with me if I now write this left hand side or this right hand side as mu 0, the first term being over a surface JC dot ds. Remember, this JC that I am writing is the current density. All right, but the density that I have calculated in this scenario is the surface density. All right. In following the same argument, I can also write this current as a surface density with the help of a surface density, which I will be calling as JD, isn't it? I can also write this as across the same surface, across the other surface. This is JD dot ds, right? I hope all of you are agreeing with me. But if I now ask you, what is the value of this JD? What is the value of this surface charge density of the displacement current? Now, then let me just show you that total ID is what? Epsilon 0 area of the plate into del E del T. Now, if I want to know the surface charge density, all I can do is very easily, I can divide it by the area and that will give me my JD. Am I right? All I have done is I have started from the current and I have divided it by the area, and the area in this case is nothing but the area of the plate. So in this case, what am I going to get rid of? I'm going to get rid of the area. So epsilon 0 del E del T is nothing but the surface charge density or surface current density, but which current? Displacement current. So epsilon 0 del E del T is the surface current density in terms of the surface. And epsilon 0 E, if I write together, I hope all of you will agree with me that this JD is nothing but del D del T. Right? Am I right? So from here, what I can take is this value of JD and I can place it over here. Del D, del T. Correct? I hope everybody is with me. So in this scenario, where are we standing? We are standing at the integral form of fourth Maxwell equation. So let us take a look on this once again. In the left hand side, I have line integral of b dot dl across the contour which I may have drawn across the parallel plate capacitor. And in the right hand side, I have contribution from two terms. One term being the conduction current and the other term coming from the displacement current, right? But if as a next step, obviously, from integral form, we would like to convert this to the differential form, which we have already done so many times for our earlier equations. But then see, when I compare both the sides, this side has all the surface integrals, whereas the left hand side only has a line integral. So then what has to be brought in? We have to convert this line integral into a surface integral. And reminding all of you, which law is going to help us to convert a line integral into a surface integral? It is going to be the Stokes Theorem, right? So, using Stokes Theorem on this b dot dl, what I can write? I can write this as, I can write the left hand side of this equation as surface integral of curl of b dot ds over the same surface S. Now this is equal to these two in the right hand side. And now see, we are having the same surface integral in both our left hand side as well as right hand side. So in this scenario, if I compare these left hand side and right hand side, I can equate the integrals, isn't it? And in this case, yes, Pudita, you are right. It is indeed the Stokes theorem that we have used. So in this scenario, comparing or just writing the integrals, equating the left hand side and right hand side integrals, I will be getting curl of B is equal to Jc, obviously with a mu 0 Jc plus del d del t. And here we are. This is our so-called differential form. So from the integral form, we have brought in our differential form that curl B is equal to mu 0 times Jc plus Jd, and Jd is nothing but del D del T. So have you all followed how from the integral form we have derived our differential form? And let me just point it out to you that the contribution in this case, the contribution is from two terms, one being the conduction current density and the other being the displacement current density. Fine. Now I want to discuss about the physical significance of this particular law or this statement, what am I going to tell you all? First and foremost, let's see, this particular equation is explicitly time dependent, right? So this once again is not a steady state equation. This will vary with time. Remember when we discussed about the first two equations of Maxwell, the equation number 1 and equation number 2, they were not having any time in them. They were steady state equations. However, the third one also, that curly is equal to minus del B del T, that was also a time dependent equation, and it also did not tell us anything to do with the steady state. So the fourth as well as the third are not steady state equations, they vary with time. This is one of the physical significances that we may draw. And the other point which I want you all to understand is that production of this magnetic field. This magnetic field has been produced not only by the moving charges but also because of the time change of an electric field. This D is having epsilon 0 E, and this E was, remember, changing with time because of the AC source. So not only the general conduction current or the movement of charges which can produce a magnetic field effect, rather this new type of current which we called as displacement current is also capable of producing a magnetic field. And both of their contributions actually gives rise to this so-called magnetic field as was observed in the experiment as well. So as a physical significance, we can draw the inference that production of magnetic fields can be done, one, with the help of a conduction current, and two, by a by a time variable electric field as well. So is this understood by all of us? This particular equation actually ends up our topic of Maxwell's equations, where we have discussed all the four. Just summarizing the entire thing that we have written. Remember, how can you make yourself remember this? The first law is divergence of E. The second law is divergence of the law, rather the equation, if I say so. The third is curl of E, and the final is curl of B. So we are just changing E, B, divergence first, curl second. So if you just think in this manner, you can always remember which one is the first equation, which one is the second equation. Right. Now here, there is a very small point which I would also like to add. Say first, let me write down all of these things. So if I ask you now, I hope all of you will be able to tell along with me that divergence of E as we have written is what? Rho V by epsilon 0, where rho V is the charge density, volume charge density. We have seen the divergence of B is 0. Then we have seen curl of E is minus del B del T. And divergence, this curl of B is this particular effect. Now, please see over here that the constants that we have used here, epsilon 0, mu 0, this tells us that all this entire thing has been done in free space, in vacuum. Correct? Now, if I ask you that you will see that convert this entire thing in a medium. say instead of this free space that we have been discussing, how will the Maxwell's equation look in a medium? In a medium where the permittivity is mu, permeability is mu and permittivity is epsilon. Then all you have to do is to change or write instead of epsilon 0, you will write epsilon. And instead of mu 0, you will write mu because the entire thing is now in a medium of these constants. Fine. Now, there is another very, very important thing to be considered that say now I want to talk about these things in complete vacuum where there is nothing, right? Then what will happen? In case I have gone into a complete vacuum state, can there be the presence of charges in it? I hope you will agree with me that in complete vacuum, there can be no charge. So in that scenario, divergence of E also will be equal to 0, right? It will also be equal to 0 since there are no charges over there to produce this divergence, whether positive or negative. So in complete free space, the first equation also will be divergence of E will also be coming out to be 0, and obviously everywhere universally this divergence of E is always supposed to be 0. And not only, since remember the other day also I was telling you all that not only in an experimental setup or whenever there is a so-called current, these Maxwell's equations are valid. These Maxwell's equations are valid for the entire electromagnetic radiation. Electromagnetic radiation as in wherever, whichever wave has the contribution of the electric as well as the magnetic fields. And whenever there is this kind of a setup anywhere, not because of say the so-called conduction current only, the so-called movement of charges only, wherever there is this electromagnetic radiation possible, these four equations will hold. Which means if there is a time rate of change in magnetic field, an electric field will be produced. Whenever there is a time rate of electric field like this, a magnetic field will be produced. So see, time changing magnetic field can produce electric field, time changing electric field can produce magnetic field. So like this, Maxwell's equations are actually very, very important from the point of view of the overall physics as well in terms of the electromagnetic radiation entirely. Okay, so I hope with this we are now done with the entire part of syllabus which we had to study. So this is where I would like to end today's class. I hope you all had understood everything, and as for the comments that I see, everybody has understood. So that's all for today. Bye. Bye bye all of you.